All right, in chapter 8, section 6, we're going to continue talking about vectors, but we are going to transition our view from what we were talking about in 8.5. In 8.5, we took a geometric view of vectors. In 8.6, we are going to coordinatize vectors and talk about them more as an algebraic type component. So we got some definitions to help us out with that. So a vector is in what is called standard position if its tail is located at the origin. So we have a vector that looks like this, and the vector v can be written as a comma b, and notice instead of using the parentheses like we do with ordered pairs, when we put the angled brackets on, it means we're talking about a vector. This notation means that the head of the vector is located at the point AB. So the head is going to be at A, comma, B. So in this notation, the tail is always at the origin. So the tail is located at 0, 0, and the head is at A, comma, B. So when we see that notation, we know that the tail is always located at the origin, which means that the vector is then in standard position. The component form of the vector AB with A equal to tail x1, y1 and B equal to head x2, y2. And I know that A was the tail and B was the head because the end of the arrow, the one without the point, is over the A, and the part of the arrow is over the B. So that would mean B is the head, and A is the tail. So this is our head, and this is our tail. So the vector AB in component form is x2 minus x1, comma, y2 minus y1. And in words, we say it is the head minus the tail, because the head coordinates are the ones that are listed first, and we subtract off the coordinates from the tail. So in this form, the scalar A, and we're going to call this thing here A to be consistent with what we had above. And we're going to call this B. The scalar A is the x component of the vector. The scalar B is the y component of the vector. So when we use component form, this will always put the vector in standard form or standard position. So the net effect of this, when you do head minus tail, is it gives you an equivalent vector with its tail at the origin. Let's take a look at example number 1. So we wish to find the component form of AB. So this is going to be our head, and this is going to be our tail. So our vector is going to be 5 minus 4, comma, 6 minus 1, which gives us 1, comma, 5. So that would be our component form of our vector AB. All right, it's now your turn. Alright, so for our U-try, we're once again going to do head minus tail. So in this case, it is going to be 3 minus a minus 2, comma, negative 6 minus 4. Minus minus gives us plus, so we get 5 and negative 10. Alright, so let's go ahead and actually just draw couple of pictures. So if I were to draw AB, it starts at 4 comma 1, so I go over to 4, 1, so that's its tail, and its head is at 5 comma 6, which is this right here. And if I draw this vector 1, 5 with its tail at the origin, I go over 1 and up 5, I get 2 equivalent vectors. Similarly, if we do the one that you guys just did, we have negative 2 and positive 4, and 3 and negative 6 is all the way at the bottom down here. And if we play connect the dots, we get this. And if we put it in component form, we go to 5 and negative 10. And we get a vector that looks like this. So turning a vector into component form is really just translating that vector to having its tail at the origin and creating an equivalent vector. It turns out for vectors that being able to move them around like this is very helpful because they're translation invariant, which means we can do all of our arithmetic or all of our math with vectors that we've translated to the origin and still get the same answer, which will make our work in the future a lot easier. So instead of doing things geometrically like we were doing in 8.5, we can use algebraic methods to help us simplify what's happening. All right. All right, so the magnitude, or the length of a vector in component form, is denoted by what looks like an absolute value symbol. So we put vertical bars So it is worth noting some texts do use double vertical bars. So if you see double vertical bars, it means the same thing. And the magnitude of a vector is the square root of v1 squared plus v2 squared, where v1 and v2 are the components of the vector v. So this is really just the Pythagorean theorem. Because if you think about what we have, if we have a vector with components v1 and v2, then the hypotenuse is v1 squared plus v2 squared, and the square root, which is the magnitude of that vector. So since we know that our vector in this form is in component form, which means its tail is at the origin, we can just use the Pythagorean theorem, which is a squared plus b squared equals c squared, to get the length of the hypotenuse, which is the square root of the sum of the squares of the components. Two vectors are equivalent if and only if their components are equal. So in symbols, vector v equals vector w if and only if v1 equals w1 and v2 equals w2, when v is v1, v2, and the vector w is w1, w2. So that's our definition of equality. And the algebra of vectors says that if c is any real number and v is equal to the vector v1 and v2, then the scalar c times the vector v says we multiply each component of the vector v by the scalar c. All right, so in example 2, we have the following vectors. Use v equals 3, 1 and w equals negative 2, 5 to find the following. So negative 3 times v. So that's negative 3 times our vector v. And our rule here says that a scalar times a vector says we multiply each of our components by that scalar. So negative 3 times 3 is negative 9. Negative 3 times 1 is negative 3. So negative 3 times v is the new vector, negative 9, negative 3. And the effect was we just took all of the components of v, so 3 and 1, and we multiplied them by negative 3. So now b says, well, what is 0 times w? Well, 0 times negative 2, 5 would be 0 times negative 2, 0 times 5. And 0 times anything is 0, which would give us the vector 0 and 0. All right, lastly, we have a u-trie with 2 times w. So 2 times w is going to be 2 times negative 2, 5. So 2 times negative 2 gives me negative 4, and 2 times positive 5 gives me 10. So the product of 2w is the vector negative 4, positive 10. The next thing we want to talk about is addition of vectors. So vector addition and subtraction. So if v is equal to v1, v2, and w is w1, w2, then vector v plus w is v1 plus w1 and v2 plus w2, and then v minus w would be v1 minus w1, v2 minus w2. So we're going to add and subtract vectors in the same way that we would think. All right, so let's take a look at example 3, part A. And notice that it has a mixture of both scalar multiplication and vector addition and subtraction. So let's go ahead and write this out. So we have 4 times v. So 4 times 1 comma 2 minus 2 times negative 3 and 5. So we do our scalar multiplication first. So that gives us the vector 4 comma 8 minus 2 times negative 3 is negative 6 and 2 times 5 is 10. And then we subtract. So that's going to be 4 minus a minus 6, comma, 8 minus 10. Minus minus makes it plus, so we get the vector 10 and negative 2. So 4v minus 2w gives us the new vector 10, comma, negative 2. Part B says, find the magnitude of 4v minus 2w. So luckily, we just found this part here, and our definition of the magnitude of a vector is the magnitude of v is the square root of the sum of the squares. So from A, we have the following. So the magnitude of 10 negative 2 is going to be the square root of 10 squared plus negative 2 squared, which is going to give us the square root of 100 plus 4, so the square root of 104. And 104 breaks down into 4 times 26. And the square root of 4 is 2, so we get 2 square roots of 26 would be our simplified magnitude. So it's worth noting the magnitude is a scalar. So when we find the length of a vector, we're finding a scalar. It no longer has any direction associated with it. All right. So the next one is U try C, which wants us to calculate 6v plus 3w. All right, so we start with 6 times our vector 1, 2 plus 3 times our vector negative 3 and 5. So that gives us 6 and 12 plus negative 9 and 15. So 6 plus negative 9 is negative 3, and 12 plus 15 is 27. So 6v plus 3w should give us negative 327. So far we've multiplied a vector by a scalar, and now we've added and subtracted two vectors together. There is another product for vectors called the dot product. So the dot product of two vectors is, if we have vectors v1 and v2, and vectors w1 and w2, the algebraic definition of the dot product is v dot w is v1 w1 plus v2 times w2. So notice that the dot product is a scalar and not a vector. The geometric definition of the dot product is v dot w is the magnitude of v times the magnitude of w times the cosine of the angle in between the two vectors. The geometric form is often used to find the angle between two vectors. Solving for theta gives that theta is equal to the inverse cosine of v dot w divided by the magnitude of v times the magnitude of w. So the dot product of two vectors is given in these two forms. We have the algebraic form and we have the geometric form. And we can use either of these to calculate the dot product depending on what information is given. And as noted, the geometric definition is often used to find the angle in between two vectors. So if we know two vectors, we can find the angle in between them by using the dot product in its geometric form. So let's go ahead and do some examples involving the dot product. So example 4, it says use u equals -2, 1, v equals 1, 2, and w equals -3, 5 to find the following. So A, we want to find v dot u. So v dot u is going to be it's going to be v1 times u1. So v1 is 1 and u1 is -2 plus v2, which is 2, times u2, which is 1. Which gives us -2 plus 2, which is equal to 0. So v dot u is equal to 0. Part B says find the angle in between the two vectors. Well, that means we're going to use this geometric definition, which is v dot w over the magnitude of v and the magnitude of w. So to use that formula, we're going to need v dot u, which we calculated already. So we have v dot u is 0, but we also need the magnitude of v, which is going to be 1 squared plus 2 squared, which is the square root of 5, and the magnitude of u, which is going to be the square root of -2 squared plus 1 squared, which will also be the square root of 5. So then, putting all of that into our formula, theta is equal to the inverse cosine of v dot u all over the magnitude of v times the magnitude of u. So that's the inverse cosine of v dot u was 0 over the square root of 5 times the square root of 5. Well, that gives us the inverse cosine of 0 over 5, which is the inverse cosine of 0. And the inverse cosine of 0 is 90 degrees, or pi over 2. So then that would tell us that the two vectors are perpendicular. So that is an interesting fact. Two vectors u and v are perpendicular. If and only if u dot v is equal to 0. So once we found out in part A that v dot u was 0, we would have known immediately that the vectors were perpendicular. But in part B, we actually calculated the angle, which was 90 degrees, which tells us that they are perpendicular. So that is a special property of the dot product, that if you dot two vectors together and get 0, we know that they are perpendicular. All right, so now we're at a u try. So let's have you guys go ahead and find v dot. All right, so to calculate v dot w, we're going to do v is 1 comma 2 dotted with w, which is -3 and 5. So that's going to give us 1 times -3 plus 2 times +5, which is -3 plus 10, which will give us 7. So when we do our dot product, we're really just multiplying the components that are the same together. So the first components together, the second components together, and then adding all of those up. And that gives us our -3 plus 10, which is 7. The next thing we want to talk about is a unit vector is a vector with magnitude 1. Just like a unit circle was a circle with radius 1, a unit vector is a vector with magnitude 1. So in symbols, we write the magnitude of u equals 1. The process of converting a vector into a unit vector is called normalizing the vector. The unit vector u in the same direction as vector v is given by the following formula. So u as a unit vector is equal to 1 divided by the magnitude of v times v. So this would be a unit vector that has the same direction as the vector v, but it has length or magnitude 1. So example 5 says, find the unit vector in the same direction as w. So to use our formula, we need to calculate the magnitude of w, which is going to be the square root of -5 squared plus 12 squared, which is 25 plus 144, which is the square root of 169, which is 13. So then our unit vector u is equal to 1 over the magnitude of w times the vector w. So 1 over the magnitude of w is 13 times our vector w, which is -512. So now we have our scalar multiplication. So that's -5 over 12 or -5 over 13. Sorry. That's a 13. And then 12 over 13. So our unit vector is -5/13 and 12/13. So that has the same direction as the vector w, but it has only length 1. All right. So there are some special unit vectors, and I hinted at these earlier. And the two special unit vectors are I hat and j hat. So they are written as either a bold I, or to signify it as a vector, sometimes they put the hat on them. And either way, we read this as I hat and j hat. So I is the unit vector parallel to the positive x-axis, and j is the unit vector parallel to the positive y-axis. So in symbols, I hat is the vector 1, 0, and j hat is the vector 0, 1. So every vector v, which has components v1, v2, can be written as a linear combination of I and j, as v is equal to v1 I hat plus v2 j hat. Because this was the part that was parallel to the x-axis, that's the x component of the vector, and j is the y component of the vector. So it's just a different way to write vectors in a component form. And so both of these have their uses, but the two notations mean the same thing. So let's take a look at our next example. So keeping that in mind, that it is just a different way to write the vectors, will help us make sure we get the correct solution. So we want to use the vectors 2, 3, and w is negative 3, 5 to find the following. Write v and w as linear combinations of I and j. Well, so then the vector v would be, well, v's x component is 2, so we're going to have 2 times I hat, plus its y component, that's its second component, 3 times j. Our vector w is going to be, its x component is negative 3 I hat plus 5 j hat. So it's really just a different way to write the vectors u and v. So we can see that vector v still has components 2 and 3, and vector w still has components negative 3 and 5 respectively. So now when we add vectors in this new form, we're actually just collecting like terms. So we would have 2i plus 3j plus our vector w, which is going to be negative 3i plus 5j. Well, then we just collect our like terms, just like we have always done in algebra. So we have our I hats and our I hats. So 2 plus negative 3 gives us negative 1 I hat. And then 3j plus 5j gives us 8j. And then, as we would with polynomials, if we have a 1 coefficient, we wouldn't write it. So we would just finally write our final answer as negative I hat plus 8 j hat. So this is just a different way to do the same thing. And if we notice, 2 plus negative 3 gives us negative 1, and 3 plus 5 gives us 8. We're just writing these in a different format, but it means exactly the same thing. All right, it's now your turn. I want you to do w minus v and be just a little bit careful when we're subtracting. All right, so to do w minus v, we're going to have negative 3i plus 5j minus 2i plus 3j. So then we distribute our minus sign into our parentheses. So that gives us negative 2i minus 3j. And then we just collect our like terms. So negative 3i minus 2i gives us negative 5i. And 5j minus 3j gives us 2j. And that would be our solution. All right, so it is often helpful to be able to decompose a vector into its components, as we saw in the last section. Turns out there is a nice formula that we can derive to help us do so. So if we have our vector v here, and we know its magnitude, so we have the magnitude of the vector v, then we can talk about the components of this vector. So we would have our y component and we would have our x component if we know our angle theta. So then if we wanted this component right here, the x component, or the I hat component, that would be adjacent and hypotenuse. So that would tell us that this side is going to be the magnitude of v times the cosine of theta. And the vertical component, or the j hat component, is going to be the magnitude of v times the sine of theta, because that is opposite over hypotenuse is sine, and adjacent over hypotenuse is cosine. So in terms of our triangle, we would have the magnitude of v cosine theta and the magnitude of v sine theta. Both of these would have a common value, or a common factor of the magnitude of v. So if I write the vector v in terms of these components, it would be the magnitude of v times the cosine of theta I hat plus the magnitude of v times the sine of theta j hat. If I factor out my common factor of the magnitude of v, which is missing from my formula down here, we would have then cosine theta I hat plus sine theta j hat. So we can write the vector v in its component form, where we have our part parallel to the x-axis and our part parallel to the y-axis, using this formula. So any vector v can be written as its magnitude times the cosine of theta I hat plus the sine of theta j hat. And that will give us our vector in component form, which will be helpful in our next example. So example 7. An airplane travels at a bearing of 100 degrees at an airspeed of 190 kilometers per hour, while a wind is blowing 48 kilometers per hour from 220 degrees. Find the ground speed of the airplane and the direction of its course over the ground. So let's draw a picture to help us see what's happening. So we have our coordinate system, and we have our airplane. Travels at a bearing of 100 degrees at 190 kilometers per hour. So we know that that's 100 degrees. And we know its speed is 190 kilometers per hour. So that means its magnitude is 190. We then have, when the wind is blowing 48 kilometers per hour from 220 degrees. So we have to be a little careful with that. So we have 220 degrees. And it is 48 kilometers per hour. But it's not blowing to that angle, it's blowing from that angle. So we'll take care of that in just a second. So let's write our vectors for each of these. So our vector for the airplane is going to be its magnitude, which is 190, times the cosine of 100 degrees I hat plus the sine of 100 degrees j hat. And for our wind, we're going to have 48 times the cosine of 220 degrees I hat plus the sine of 220 degrees j hat. So since the wind is coming from (220 degrees), we will subtract the vectors. So we want A minus W which, if we write them in our component form, distributing the 190 in, we're going to have 190 cosine 100I plus 190 sine 100j minus 48 cosine 220I plus 48 times the sine of 220j. So we collect our like terms. So we have 190 cosine 100 minus 48 cosine 220, and that's our I, plus 190 sine 100j minus 48 times the sine of 220j. Sorry, that's too many j's. There's one j for both of them. So we just gathered up our, so we have our I components, so I, and then we had our j's that went together. So j and j, right? So now at this point, we need to just put this into our calculator. So we grab our calculator. So my first component is going to be 190 times the cosine of 100 minus 48 times the cosine of 220. And I'm going to store that in my calculator as B. And I'm going to do the same thing with the next one, 190 times the sine of 100 minus 48 times the sine of 220. And I'm going to store that in my calculator as C. So I've got each of these in my calculator now. And I can use them to answer the questions. So the first thing we were asked is to find the ground speed of the airplane and then its direction over the ground. So the ground speed is going to be the magnitude of the vector So in terms of our stuff, we're going to have the square root of b squared plus c squared. So the ground speed is 218 kilometers per hour. And then the direction that it's going in is going to be the direction of this vector. So whatever it is, we have B and we have C. So we have our resulting vector, whatever it is. So if we were to draw a quick sketch, I don't know exactly where it is, but it's going to be hat components B and C. So if we want the angle, we're going to need to do the inverse tangent. So the inverse tangent of this case is going to be C over B on our calculator. So inverse tangent of C divided by B. And we get 89 degrees. So if we go back and look at our question, we see that the plane was flying at 100 degrees. The wind was actually coming from this, so it was blowing in like this direction. So it blew the plane a little over 10 degrees to where it was going at 89 degrees, so it was almost going right up the y-axis, is what our solution here was telling us, that it went at 89 degrees. All right, so we've got one more example. Example 8 says that a 600-pound block is suspended by two cables as shown below. At point B, there are three forces acting R, S, and W. Find the tension in each cable. So our goal is going to be very similar to what we did in the previous problem. We're going to need to decompose these vectors, all three vectors, into their components, and then we're going to use the following key idea. So our key idea since the crate does not move, the sum of all the forces must equal 0. So what that means then is that if we find the vector r, the vector s, and the vector w, and we add all of them up, this has to add up to 0. So let's go ahead and find each of these forces. So we're given some angles, but we need to have the angles as measured from the positive x-axis. So if this angle is 60 degrees, the measure to get to angle R is going to be 180 minus 60, so that's going to be 120. And then the measure to get all the way down to W is going to be 270. So if we do our vector S, we don't know its magnitude, so it's going to be the magnitude of s times the cosine of 40 degrees I plus the magnitude of s times the sine of 40 degrees j. If we do our vector r, it's going to be the magnitude of r times the cosine of 120i plus the magnitude of r times the cosine of 120 degrees j. And then lastly, our vector w is going to be, well, we know its magnitude. It is 600 times the cosine of 270i plus 600 times, oh, I typoed on the previous one, that's a sine, 120, and then this is going to be the sine of 270. And j. So now, if we were to add all of these together, we get the magnitude of s times the cosine of 40 degrees plus, collecting our i's, so that's really these guys right here, plus the magnitude of r times the cosine of 120 plus 600 times the cosine of 270, and that's going to be our i's, plus, now we do the same thing for our j's over here, so we're going to have the magnitude of s times the sine of 40 degrees plus the magnitude of r times the sine of 120 degrees plus (600) times the sine of 270 degrees. And that's going to be our j. And then if we add both of these up, it's supposed to equal 0, which is 0i plus 0j. So this is a system of equations for each of these. So basically, this has to be 0, and this has to be 0. It turns out that we can simplify this last piece a little bit. The cosine of 270 degrees is 0, and the sine of 270 degrees is negative 1. So this gives the system of equations the magnitude of s cosine 40 degrees plus the magnitude of r cosine 120 degrees plus 0 equals 0. And the second one is the magnitude of s times the sine of 40 degrees plus the magnitude of r times the cosine of, or times the sine, why do I keep wanting to do cosine? Times the sine of 120. And then minus 600 is equal to 0. Well, moving that 600 to the other side would give us equals 600. So we can actually write this as a matrix. So we're going to move to the other side. And that will give us positive 600. So we add 600. We add 600. So if we write as a matrix, we get cosine 40 degrees, cosine 120 degrees, and 0. And we get the sine of 40 degrees, the sine of 120 equals 600. And then we can put this in our calculator and RREF this thing. So we go second matrix, we go over to edit, and it's going to be a 2x3 matrix. And we put in our cosine of 40 degrees, our cosine of 120, and 0. And then we have the sine of 40, the sine of 120, and 600. We go second matrix, over to math, down a whole bunch of times to find RREF, and then second matrix, A, press enter, and we get our two solutions. So this is going to be our S, and this is going to be our magnitude of R. So S would be about 305, and R would be about 467. And that would be our solutions to that equation.